Okay, we're back talking about series circuits. We just got done saying that the current in the series circuit is the same at all locations. That doesn't mean it can't change if the voltage or one of the resistances change, but if you look at a series circuit, any series circuit, and you measure the current at two different places, it will be the same. Okay, it will be the same everywhere in the circuit, and that makes sense because there's only one path for the current to flow through. There's only one way that the electrons can move, and electrons aren't like cars approaching like an accident on a highway. They don't get backed up. There's a steady flow all the way through a circuit. And to help you remember that, on the reference tables, there is this equation right here. I equals I1 equals I2 equals I3 equals ... That's just to remind you that the current is the same at all locations. So I'm going to write that down for you as well. I equals I1 equals I2 equals I3 equals ... Current everywhere in a series circuit is the same. Let's move on. Two more topics. Individual resistors. For any resistor, the ratio R equals V over I is a set number that does not change, no matter how much current goes through the resistor. Because of this, we say that resistors follow Ohm's law. Remember, that's the equation that brought us Ohm's law. R equals V over I. I just multiply the I by both. I multiply both sides by I, and I get Ohm's law. Remember, Ohm's law is really just the definition of resistance, okay? We can measure voltage drop, we can measure current, and the ratio of those two is the resistance. Once we know the resistance, it turns out that that resistance doesn't change no matter what we do to the current or the voltage. To demonstrate, let me show you. Let's take a look at this. So this is the circuit from before. Let's take a look at the 7 ohm resistor, okay? So let's find the voltage drop across that 7 ohm resistor. Okay, 3.33. And let's look at the current, 0.48. Okay. So this won't, if I turn up the voltage, or if I increase the voltage gain for the entire circuit, that will increase how much voltage drop there is with this resistor. Matter of fact, it will change the voltage drop at all of my resistors. And it will also change the current. So let's say I want to increase the voltage drop from 20 to 40. Look at these numbers, remember what they are. And notice that if I were to take the voltage drop of 3.33 and volts and divide it by the current, 0.48, I get approximately 7. Okay, voltage drop divided by current through a piece of circuit is that piece of circuit's resistance. So this says it's about 7, 6.93. Now that ratio shouldn't change no matter what I set this to. Let's do this really easy. Let's double the voltage for the entire circuit to 40. Okay, so this is for the entire circuit. Look at what the voltage drop for this resistor is now. 6.67 voltage drop around this, and the current is 0.95. Notice that they both approximately doubled. Now, if I take 6.67, oh, that's not what I wanted. 6.67 divided by 0.95. Notice I still get a resistance, the ratio of voltage drop to current of about 7. Matter of fact, I could set this voltage to the overall series circuit voltage to anything. Let's crank it. Let's crank it all the way up. Let's have some fun. 120 volts. Notice that my voltage, oh, I can't even read that, is now 20 volts. The voltage drop here is 20 volts. And the current is 2.86. If I do 20 divided by 2.86, once again, I get approximately 7. Okay? So what we're seeing here is that the resistance does not change as we increase the voltage drop for a resistor. That is a special property. That is called something being ohmic. Okay? Ohmic is the property where the voltage or the resistance does not change as the voltage drop and current change. Okay? So resistors are ohmic. Last one, equivalent resistance, and the last equation on that series circuit section. The equivalent resistance or total resistance of a series circuit is given by the following equation. Okay? right here in the reference tables. REQ equals R1 plus R2 plus R3 plus ... Okay. Now what this means, equivalent resistance. Equivalent resistance really means kind of like the total for either, or really for the entire circuit. You can also find equivalent resistances for parts of a circuit, but we're usually, because we're going to deal with very simple circuits, equivalent resistance to us means what's the resistance of the total circuit, the circuit as a whole. In essence, what it really means is imagine you could combine all these resistances into one big resistor. How much resistance would that resistor have to do the exact same thing that these 2 or 3 or 4 or whatever individual resistors do? Now, let's see how we can figure out the equivalent resistance, or how we can check this. Let's go back to our screen. Now, the equivalent resistance, yeah, you can get it by adding up all these total. And I'll do that in a little bit. But what I also want to point out to you is that if you think of the equivalent resistance as like the overall resistance of the circuit, or if you were to replace all of these resistors with just one big resistor, you can actually figure out or use the equivalent resistance to figure out and relate it to the total voltage drop for the circuit, in other words, the voltage gain of the battery, and the current that flows through the entire circuit. Now, obviously, for a series circuit, that current that flows through the entire circuit is the same everywhere. But here's what I mean. The overall voltage, the voltage gain for the battery, therefore the voltage drop for all of my resistors, is 120 volts. Okay? The current in this circuit is 2.86. If I do R equals V over I, and I do 120 divided by 2.86, I get an equivalent resistance of approximately 41.96, so very close to 42. And notice what happens if I add 25, 7, and 10. 25 plus 7 is 32, plus 10 is 42. So I can find the equivalent resistance by adding up all the resistances, or I can take the total voltage and divide by the total current. And this will be the same even if I change how many resistors or what the resistance is, as long as I keep it in series. Let me delete this. We don't need this anymore. And I just have an equivalent resistance of what? 32. Notice that the current has changed. If I were to now do 120 divided by 3.75, this should be about 32. It's exactly 32. Okay? So there's a little bit about equivalent resistance. Oh, there we go. Okay. So let's look at some examples. Let's look at some actual examples. Okay? Our first example is we have a voltage drop of 6 volts, a current of 0.02 amps. What is the resistance? Well, this is pretty easy to do. We know Ohm's law. This is a resistor. We know that this resistors are ohmic. So we simply do V equals IR. The voltage drop is 6 volts. The current is 0.02 amps. We're just solving for the resistance. What should the resistance of this resistor be? 6 divided by 0.02 is 300. And remember the symbol, the units for resistance, is that funny little horseshoe shape. That's an ohm. Okay, ohm is the unit of resistance, a volt per amp. 300 ohms. Now that was pretty easy to do by itself. Let's actually look at a simulation and make sure that this works. Now the tricky thing with our simulations is the resistances, unfortunately, don't go all the way up into the hundreds like we want. They stop at 120. But we can still get an idea to see if this is right or not by, if we can't get the full resistance, why don't we instead just use maybe like a tenth of that resistance? So we got the resistance to be 300. A tenth of 300, this should be very easy for you to do, is 30. So let's make the resistance of this resistor 30. Oh, I had it. There we go. Okay, and it's not connected yet. Notice that I'm all set to measure the current and the voltage as soon as I actually connect this circuit up. Now, if I decreased the resistance by a factor of 10, if I cut it into 1/10 the size, and the voltage stays the same, notice I had the 6-volt battery, what should happen to the current? It should be 10 times as much. I cut this in 1/10. If I multiply this by 10, I'll still get 6. So multiplying 0.02 by 10 should give me 0.2. So this is a way to kind of get around the fact that this simulation is a little bit limited. If I now just connect my wires, take a look at the voltage drop and the current. Aha! We have a voltage drop of 6, we have a current of 0.2 amps, resistance of 30, just like we predicted. This works out. Perfect. Let's look at our second example. Current 0.005 amps, resistance 700 ohms. What's the voltage drop? Again, we know that Ohm's law should work out. V equals IR. And let's see, I know the current, 0.005 amps. I know the resistance is 700 ohms. What is the voltage? .5 volts. In other words, there should be a 3.5 volt voltage drop with this circuit. Again, let's go to our simulation. So let's see here. Here's how we're going to do it. I like to change, the battery is the easiest thing to change because it's very easy to change the resistance and the voltage here. So we'll just measure the current to make sure that we got the right idea. The resistance, let's see. Let's set the battery to be 3.5 just like they had it. Let's see, too far. Okay. And again, instead of a 700 ohm resistor, we can't go up to 700. Let's go to 70. Let's cut it in half. There we go. Okay. Now, if we're correct, our current, since we cut, I'm sorry, we didn't cut it in half. We cut it in as a tenth. If we cut our resistance by 1/10. Let me rephrase that. If we made our resistance 1/10 the size it should be, our current should be 10 times the size it should be. So we're expecting our current to be 10 times 0.005, maybe 0.05 amps. And we connect. Our voltage drop is 350, just like we said. Resistance of 70. We get 0.05 amps. Perfect. Last one. We want to know a couple different things. We want to know the equivalent resistance and we want to know the current. So the equivalent resistance here, since we have 3 resistors, is simply given by Req. And yes, you do have to write this formula. R1 plus R2 plus R3. That's just equal to 20 ohms plus 40 ohms plus 60 ohms. 20 plus 40 is 60. 60 plus 60 is 120 ohms. Now, if the voltage drop across this entire thing is 6 volts, then what is the current? So, I've got this set up, 20, 40, 60, and a 6-volt battery. Again, I use Ohm's law. I'm going to do VT for V total drop. I guess the T is not super necessary, but I like to add it in there. The total voltage drop across all 6 of these is 6 volts. The current is what we're looking for, and the Req is 120 ohms. It's not a 6-volt drop across just one, it's a 6-volt drop across all of them, so we have to use the equivalent resistance. Imagine just taking these resistors and like squishing them together. They would look like one resistor with a resistance of 120. So I do 6 divided by 120. I get 0.05.